Now in this equivalent two winding transformer, what is the turn ratio here? Okay, so if you see the turn ratio, it would be, the turn ratio would be N1 minus N2 upon N2, right? So equivalent turn ratio here is N1 minus N2 upon N2. And since we have defined N1 by N2 as A, so this is A minus 1. Okay. In two winding transformer, it was A, right? N1 by N2. But now here, you can see that it is A minus 1. Now we will see the equivalent circuit diagram of a practical autotransformer. So since we have energized from the primary, I'm just drawing the first the winding configuration. So for a step down, and this is connected to the load, right? So obviously the induced EMF is in this winding as well, where whose number of turn is N1 minus N2, and here the number of turn is N2, and this entire one is N1, right? So here the induced EMF in this upper portion between A and B, it would be E1 minus E2, right? And here the induced EMF in N2 would be E2 only. Okay, so I'm redrawing it along with the series impedance. I'm assuming that shunt, the magnetizing current and even the core losses component would also be there, but currently I'm not considering it. I'm just showing the simplest version of it. So if you'll see that along with the for this winding, I can represent it by a resistance. Okay, so generally this winding, the upper portion, is known as series winding, and because the current is flowing in this from primary towards the, from the source to the load, one current is actually flowing in this branch as well, right? So we will say that this is a series branch, this is the convention, and this is the common winding. Okay, so this is common winding and this is series winding. Okay, so for this I am representing, let's say for series SE, I am representing the winding resistance and the leakage reactance JXSE, and obviously the induced EMF would here be E1 minus E2, where E1 minus E2 is actually equal to 4.44 F5M N1 minus N2. And then you have the, again I would say, RC for the common winding, and then JXLC, and again a voltage source, right? And this is E2, and this is actually connected to the load. Okay, so if I draw the, because we have a concept of two winding transformer, so I will try to solve the we'll try to draw the equivalent circuit diagram of this auto transformer based on that two winding transformer knowledge which we have developed till now, right? So since we say we know that the transformer action is happening between these two portion, between portion AB and BC, so I'm bothered about this configuration only. Okay, so let's say, so this would be the winding resistance, leakage impedance of the series portion RSE, and JXL, I would say JXLSE, this is XLSE, XLC, right? And let's say for time being, obviously you can think of the core losses here and the magnetizing reactance here. For the sake of simplicity, you can even ignore this as well. Okay, and then you have the transformer action, right? And what is the turn ratio here? So the turn ratio is A minus 1 now, because this winding is, we have seen before that this is N1 minus N2, N1 minus N2, and this is N2. Obviously, here also you will be having the leakage, the series impedance, so resistance RS, I would say RC for the common winding, and JXLC for the common winding, and then you have the load connected here as well. Okay, so obviously if you want to, and this is the voltage here, which is, let's say, V2 here, and obviously here we have the E2, and this portion we have E1 minus E2, the voltage here. Here we have E2. Okay, the RMS would be E2 capital, and the small one is the instantaneous one. Okay, so now we can transfer these impedances towards the primary side. Okay, and what is the current? Current here, obviously we have seen before that current here, we said that it would be I2 minus I1. Okay, so we can transfer these impedances from the secondary side towards the primary side, and the voltage here is actually V1 minus V2, RC JXM. So RC, I would say this is RC R core, I would say. Okay, so if I transfer these impedances towards the primary side, then we can directly, and for time being I am just neglecting this, the shunt branch parameters as well. So RC dash would be given by same as, like, since we know that concept now, transformer action, we know that transformer action is happening between N1 minus N2 towards the N1 minus N2 and N2 number of turns. So turn ratio we have, we know that this is N1 minus N2 upon N2, which is nothing but A minus 1. So RC dash we can write as A minus 1 whole square. Okay, turn ratio times whole square we do, right? So A minus 1 whole square into RC, and JXLC dash would be A minus 1. Same those concepts we can build up here as well. J times XLC here, whole square. Okay, and similarly we can solve, let's say, even these problems. So we will take up one problem based on these auto transformers as well. Okay, sorry, here this is not V2 minus V1, rather this is V1 minus V2, right? Here this is V1 minus V2. So this is V1 minus V2 here. So what would be Z equivalent? If you'll see Z equivalent here, the overall impedance. So this Z equivalent would be RSE plus A minus 1 RC whole square plus J times of XLSE plus A minus 1 whole square of XLC. Okay, and what is V2 dash here? So V2 dash, it would be, you can directly say, let's say Vx, I'm referring this voltage towards the primary side, right? this V2 voltage towards the primary side. So this would be Vx upon V2, and this is equal to A minus 1, right? So Vx is A minus 1 times, so this V2 dash would be equal to this V2 dash would be equal to A minus 1 of V2. Okay. Now, can you write the KVL equations here as we have done for the two winding transformers as well? So obviously, if we want to write the KVL equation here, so it would be, let's say, V1 minus V2. Obviously, these are all in phasor quantity, right? Into I1, and this is Z equivalent here, right? I1 into Z equivalent, and then this minus V2 dash, and if we compute here, this would be I1 into Z equivalent minus A minus 1 of V2 here. Sorry, it would be plus here, right? If you want to write the KVL here, so this voltage drop plus this voltage drop is the voltage drop is the voltage V1 minus V2, right? So this is plus here. So if we solve again further, you'll see that this is I1 Z equivalent plus A times V2 minus V2. These are all in phasor quantity. So this is equal to V1 is equal to I1 Z equivalent plus AV2. So if you see, if you compare this expression with the equivalent circuit diagram of two winding transformer, so the expression looks almost same. Only difference here is the Z equivalent is different from the Z equivalent there, right? Because here the transformation ratio is not A, rather it is A minus 1, right? See here, this is A minus 1. This is A minus 1. Otherwise, the entire expression looks similar to the one which we have derived for the two winding transformer as well. Okay. So now we will look at we'll try to find the per unit impedance of the auto transformer. Okay. So if you want to write the per unit impedance of the auto transformer, so actually we need to calculate the Z base, right? And to calculate the Z base, we will assume two quantities. Let's say the S base, I'm assuming that it is the apparent power of the auto transformer. The apparent power of the auto transformer I'm choosing as the base apparent power, and VB I'm choosing, let's say, for this auto transformer, right here. So V1 is the base apparent power here, apparent voltage here. So VB is, let's say, V1. So what would be Z base here? So if you see the Z base, it would be V1 whole square upon S 80, right? So what would be Z equivalent per unit, okay, for auto transformer? So this would be, let's say, this Z equivalent, because we have seen that for this the impedance will remain same, right? So this Z equivalent, because the same equivalent impedance is for the two winding, and same impedance is there for the auto transformer as well. So this would be Z equivalent upon Z base. and this would be Z equivalent upon, so all I have referred to this Z equivalent I have referred towards the primary side, right? So this is Z equivalent into V1 whole square into SAT. Okay. Now let's say if I want to compare this impedance, the per unit impedance, when same winding, same number of turns was used as a two winding transformer, then what was the what was the per unit impedance we want to find for that? So we want this Z equivalent per unit when we were using as a two winding transformer. So we want to find this. Okay. So obviously when we were using as a two winding transformer, so obviously the base power, the apparent power rating has changed, right? So we will choose the apparent power as, let's say, the apparent power of the base apparent power for this calculation. I would be choosing the apparent power of the winding. And what would be the base voltage here? So base voltage in a two winding transformer, we have seen that this would be the primary voltage here, V1 minus V2, right? So I am using that only. So let's say this VB, I will choose as V1 minus V2. So what would be Z base here? Z base for the winding. Here this was Z base for the auto transformer. Okay. So Z base for the winding would be V1 minus V2 upon whole square. V1 minus V2 whole square upon S base. As base is nothing but SW, right? So let's say Z equivalent per unit for the winding would be Z equivalent, because all we have referred, we have seen that we have referred the impedances towards the primary side. So this would be Z equivalent upon Z base, right? Z base of the winding, and this is nothing but Z equivalent upon V1 minus V2 whole square into SW. So if we find the ratio of these two, let's say equation X and equation Y. So X divided by equation X divided by Y will actually give me Z equivalent per unit of auto transformer upon Z equivalent per unit of winding is equal to Z equivalent upon V1 whole square into SW, and in denominator for this, so this is Z equivalent, sorry, this is 80 here, S80 here, and Z equivalent Z equivalent into SW upon V1 minus V2 whole square. So this Z equivalent, this we can cancel it out here. Okay, so this is, if you'll see, V1 minus V2 upon V1 whole square into S80 upon SW. And if you further simplify it, it would be V1 upon V1 is 1 minus V2 minus, so 1 minus 1 by A, right? Whole square into S80 upon SW. And this is A minus 1 upon A whole square into S80 upon SW. And this ratio we have already calculated before, and you will see that ratio was A minus 1 whole square upon A, and that ratio was A upon A minus 1. So this ultimately becomes A minus 1 upon A. So Z equivalent for auto transformer in per unit and Z equivalent for winding in per unit is actually the ratio of these two is this. Inversely, this ratio is the inverse of the apparent power rating there, right? So that's why what I said is, so once we once we connect the two winding transformer which has the same equal number of let's say once we connect this two winding transformer with in an auto transformer with equal number of turns, then apparent power rating is increased, but the overall per unit impedance, if you'll see, that has reduced. And because of that, the fault current, if I'll say in terms of per unit, it would be more. Let's say if two winding transformer with equal number of turns, a short circuit fault occurs there. Okay, so the per unit impedance which will restrict that current would be lower if that has been connected in a auto transformer way. Okay, so as I have discussed before, though the equivalent impedances for both two winding transformer or the auto transformer, they are same, right? But the per unit impedance has reduced now. The effective impedance has reduced there. Okay, now, so this was the application where I have shown that it was we were actually stepping up the voltage, right? So this entire analysis we did when we were when we were stepping down the voltage. Now similar analysis you can do it for stepping up the voltage, right? At that time you just you just try to see what would be the equivalent impedances and these things, or the turn ratio when you are stepping up the voltage. Okay, so that I am not taking here, but even that can be calculated as well for the stepping up the voltage. I did entire analysis for the step down voltage, the step down auto transformer. You can do it for the step up auto transformer as well. And for small applications, let's say in our lab I said that we used variac, okay, or that is known as auto transformer as well, or dimmer state. So now we will discuss about variac and auto transformer or dimmer state, which we use generally in our lab. It is either single phase or three phase, but I will here just show the simple construction of a single phase. So if you see the internal construction of an auto transformer, it would be like a toroidal core, and on this core we would be having the windings. Okay, on this entire core we would be having number of windings depending upon the power rating and the voltage rating. Okay, so let's say this is the minimum voltage position here. Okay, and in somewhere in the middle around 10%, as we have talked about 1.1 or 1.2 something. So in this dimmer state or in this variac, there is a feature of even you can step up the voltage slightly higher than the voltage which is coming at the input side. So for that, what we need to do is we would be having a tapping somewhere in the middle here, somewhere here. Okay, so this is the entire the entire voltage would be actually distributed on these windings, right? Now in the center we have one rotatory arrangement. I would say this rotatory arrangement, and on this we have a carbon brush. So this carbon brush actually helps in tapping the power on these number of turns. So here let's say if this is at this position, so here you will get and how the output is connected. So this is the input arrangement. So output is connected, is tapped from here, from this carbon brush only. Okay, so one wire is this and the other wire is this ground one. Okay, and between here you can connect the load. So this is the output. Output is tapped on this carbon brush 1, which is the variable point. Okay, let's say this one. So this is the variable point. So this variable point is actually tabbed. Sorry, I would say I have made similar to this. It would be this input would be somewhere here. Okay, and this variable point you can actually vary it. So here you will be actually rotating this variable point. So it would be rotating in this direction. So till here you will get the full voltage which is you have given V input, same volt V in you will get here. Beyond these number of turns, beyond these number of turns, you will get the extra voltage there, or is the step up voltage there. Okay, so I will show a small video of this demostat which is there in our lab. That's for single phase, and similarly for 3 phase you would have 3 different stacks of it, and once you rotate on each stack, it is actually rotating the knob or the carbon brush arrangement on these 3 different, this toroidal core, and you get 3 different voltages there. Okay, so but I will show for a single phase here. Okay, so we will stop here for auto transformers, and in this auto transformer we have discussed about the working principle of the auto transformer, and then various expressions related to its the apparent power advantages, and then we have seen how the impedance, per unit impedance also varies, and then we have talked about the actual equivalent circuit diagram of an auto transformer. Okay, so we will stop here. Thank you. So this is the internal construction of an auto transformer, single phase auto transformer. You can see a toroidal core, and on that toroidal core you can see the windings has been done, and from the wire we get the input supply to it, and from these 2 terminals we get the output power of it. Output supply from these 2 terminals we get. This is the knob which we use to vary the voltages, to get the different voltages. Okay, and this is the minimum voltage position. So if you rotate it, you rotate this knob, you will get different voltages, and this is the carbon brush arrangement which is used to tap the voltage, to tap the different voltage levels. Okay, and this carbon brush is not used for high power application. Okay, for a smaller power application we can use it. So you can see this, from here we actually tap the output supply, or the current will flow from this carbon arrangement.